since we now know how to reduce a PDE to an ODE in the vicinity of a bifurcation that leads to, in this case, a stationary pattern, we can attack the problem that we have in mind where we have competing modes. Let's be concrete. Let's imagine again a pattern forming system. So in this case, let's take an equation very similar to the one before. I only add a cubic term to it, although it won't actually really matter to what we're doing, but eventually it would make a difference. Anyway, so we have now, the more important difference is that we make it two-dimensional, meaning instead of the gradient just in X, we actually take a Laplacian. And similarly here, we have a gradient instead of just d by dx. And so we make the system isotropic in the sense that all orientations are equivalent. And so if you now look at the linear stability of the state psi equals 0, so again, we linearize around psi equals 0, make an ansatz sigma psi is equal to e to the sigma t times e to the I, and now we take a wave number, a wave vector rather. And when you then plug in, you get again sigma is equal to r minus 1 minus q magnitude squared. And this growth rate does not depend on the orientation of the wave vector, only on its magnitude. And so if you look at the wave vector plane, then all the different orientations have the same growth rate. So if you now look at, again, the neutral curve, so this would be now in this case a circle. The neutral curve is a circle, and all these wave vectors have the same growth rate, like this one, like this one. They have all the same growth rate. Now that is quite confusing, or not confusing, but that's a lot, because this means that in this case, in principle, there are infinitely many different modes that all go unstable or make the basic state unstable for the same control parameter value. That's a very difficult problem. So we will not tackle that. But when you think of it, we previously also, we thought if we have actually a box, like we imagine just a square box. So let me now just draw a top view. And in that square box, length L, there you can have patterns essentially like this, or you can have them like this. Or maybe you can have both at the same time, which then looks as if it would be making squares. So therefore, the only way orientations that actually would be possible in that box would be this one in the x direction and in the y direction. And let's actually pick the length such that we don't have a high wave, many periodicities in the box, but rather we just have a box such that L in the wave number Q, the magnitude is 2 pi over L. And so then there's only one wavelength fitting in this box in each direction, so to speak, like that and like that. Okay. That's the setup. And so now we could do the same thing we did before, as in do either multiscale or do a center manifold reduction and calculate the coefficients. But maybe we can do something else instead to alleviate the algebra that gives us still some insight. And so let's first just figure out what is the form of the equations that will actually describe that system. And for that, we use essentially our symmetries, right? So there's always two ingredients. We need to first expand we need the linear modes, and we expand the solution in those linear modes. So let's do that. So we have psi would be equal to an A1 times e to the iqx. But there also would be another mode, A2, which would be e to the iqy. That would be the other orientation. And then, of course, all the harmonics. So we would have B02, which would be e to the 2iqx, and a B11, e to the iqx plus iqy, and stuff. And again, the situation will be that only this mode destabilizes the basic state and this, whereas these higher wave numbers, which have corresponding wave vectors out here, like 2qx or 2qy, or then qx plus qy would be out there, they're all damped. So maybe I should mark that here. So no, let me not mark it, it gets too messy. So that means we actually have a center manifold which is spanned just by A1 and A2, and we expect equations just for those two guys. So let's write that down. So what we expect, there's the central manifold, which is described simply by, I shouldn't say simply, it's actually quite messy, by some function f1, which depends on A1, A1 star, A2, and A2 star. And it's another equation for A2, which is, let's call it F2, which also depends on A1, A2, A1, A1 star, A2, A2, and A2 star. They also depend on our control parameter mu. I'm not going to write that down right now. So what can we say about these equations? Is there anything we can say that restricts the form of these guys? Because we know they're going to be Taylor expansions, but a Taylor expansion in 4 different variables can have a lot of different parameters if you go to cubic order. So if you can get rid of some of them, that would be definitely an advantage. So we turn to our symmetries, and there are actually 2 kinds of symmetries. Let me just, while we still have the picture here, let me put that down here in words, and then we implement them mathematically. So again, we assume we have space translation symmetry in both directions. Spatial translations. And then, in addition, let's assume we actually have a square container. So this length is really the same as that, as indicated. If it's a square container, then we have also reflection symmetries. Not just reflection symmetries as we had before. In the previous example, we had reflection symmetry x going to minus x. In this case, I'm referring more to the reflection symmetry where we flip about the diagonal. So we exchange x and y, right? So that's a square. You can also flip about its diagonal and it stays the same. And that's the other symmetry that will actually give us further information. Okay, so let's implement that. Translations. That works the same as before, except we have 2 of them. And so what we need to know what is the action of a spatial translation on the amplitude A1 and A2. We can translate in x and y independently. And so therefore, that will lead to independent actions for both of those translations. So let's do a translation x going to x plus delta x. What does that mean? That means here for A1 goes to A1 times e to the I q delta x. How about A2? A2 does not depend on x, so therefore A2 just stays put. Similarly, if we translate in y, A1 stays put, but A2 gets shifted. And these amounts by which they get shifted are arbitrary and independent of each other. So we really have 2 independent actions. We have A1 going to A1 e to the I phi 1, and A2 going to A2 e to the I phi 2. Let's go to the reflections later, and let's first implement what we learned from this. So we now know that the amplitude equations that we wrote down here, they need to be equivariant under both of these transformations independently. So let's look at the equation for A1. and require that it's equivariant under this and then after this. Okay, so what does that mean? Well, we have to write it down. Let's do the transformation for phi 1. Then on the left-hand side, we get e to the I phi 1 times dA1 by dt equals F1. A1 goes to A1 times e to the I phi 1. A1 star goes e to the I phi 1 with a minus sign. A2 doesn't do anything. So that means that this equation must be equivalent to this equation. But we know that dA by dt, dA1 by dt is given by F1. So I can replace this here by F1, evaluated at A1, A1 star, and so on, right? A1, A1 star, A2, A2 star. And so we see that the translation in X requires that if you shift inside with phi 1, the whole function f also gets shifted with phi 1. So let's write it that way. F1 of A1 e to the I phi 1, A1 star e to the minus I phi 1, A2, A2 star is equal to F, no, let me not write F1. We want to have this phase vector first. E to the phi 1, F1 of A1, A2, A1 star, A2, A2 star. So that's the first rule we have derived. That's a selection condition. So what happens if we shift in A2 and phi 2 again on F1, right? So we're not talking about F2 yet. We're just talking about F1. And now we make this transformation. So that means we shift the two second arguments in F1, but the left side does not change, right? And so therefore, if we implement the shift in Y, we have that F1 of A1, A1 star, and A2 being shifted by some phase, that has no impact. That just leaves F1 to A1, A1 star, A2, A2 star. So that leaves F1 invariant, whereas the other shift makes F1, this is actually an F1, equivariant. You get the analogous thing, of course, of F2, except it's the other way around. F2 changes its phase if you make a shift in A2, but not if you make a shift in A1. Okay, so we have that, but we need to translate that still in what it means in terms of our Taylor expansions. So let's just do it for F1, and then we see how it analogously goes for F2. So we have our Taylor expansion. So, okay, we have F1 equals, let me not write out the arguments on the left-hand side, it becomes too much. It's a sum over coefficients, alpha, m, m prime, n prime, and these are the ones for F1, times a to the m power, a star to the n prime power, a1 that is, a2 to the nth power, a2 star to the n prime power. And so now if we require this equivariance, what does that mean for our coefficients? So the shift means that on the left-hand side, the f, a shift in phi 1 makes 1 I phi 1 on the left-hand side. And inside here, we have also each A1 gets shifted by 1. So we have the condition that 1 from here is equal to m minus m prime. So that's when we shift only in phi 1, these guys get changed, and an overall factor has to pop up. When we do a shift in A2, no overall factor pops up, and so therefore we have 0 equals n minus n prime. And so that means our general term is given by, this one means that m is 1 bigger than m prime. So the factor of a1 must be 1 bigger than the a1 star. So I can write it as a1 times a1 absolute value squared. Whereas for the a2, they have to be equal. So the general term is given by a1 times a1 absolute value squared with some power, and a2 absolute value squared with some power, and of course with some coefficients, alpha. Oh, these are different coefficients, alpha and m. So that's F1. And F2 looks the same, except A1 and A2 are interchanged. And so we can write that down actually here. F2 is equal to the sum of alpha n m2 A1 absolute value squared to the nth power, A2 absolute value squared to the mth power times A2. I guess it would have been nicer to factor out the A1 here, factor out the A2 here, but okay, we've done it this way. So that's a big mess. So let's just write it down to lowest order, because we most likely will only look at the lowest orders. And the lowest orders are obviously either n is 1 or m is 1, but not both non-zero. So we get, therefore, as equations, we get dA1 by dt is equal to an A001 times A1 plus an A101 times an A1 times A1 absolute value squared plus A011 A1 A2 absolute value squared. And this would look nicer if we actually factored out this A1 here and wrote it like this, except then we have this factor. So I'm going to write it yet further. So here was an A1, which I factored out here. I also factored out an A10 if I put a parenthesis here. That means I have to divide here by A101. So that's how I can write it. And if you do the same argument for the A2, you get an analogous equation, which is A002 A2 plus A01 2 A2 times A 102 over 1012 A1 squared plus A2 squared. Okay, good. 2 cubic equations. That's what we got from translation symmetries, right? So we got rid of a whole bunch of coefficients that way, or a whole bunch of terms. So we said we have, in addition to the translation symmetry, we also have reflections. And we did use reflections in the previous analysis, which were reflections x going to minus x, and they showed that the coefficients have to be real. That's true here too. I'm not going to go through that explicitly. Let's go for the thing that's new, which is that we can also do a reflection about the diagonal, meaning we exchange x and y and see what happens then. So if we exchange x and y, so what is the action on the a's? Well, that's relatively clear. If you exchange x and y, then this x turns into y, this y turns into an x. And that's the same as saying A1 becomes an A2 and A2 becomes an A1. We just interchange the two modes. Well, I think that's not surprising. But we know now that the equations have to be equivalent under that transformation. So if we now go replace A1 everywhere here and with A2 and the other way around, we get an equation for dA1, dA2 by dt. And so that means once we replace A1, interchange A1 and A2 here, we need to get exactly that equation. Well, that means, for instance, if you exchange A1 to A2, you get an A001, but it has to be equivalent to that. So that means, let me just do it with circles. This term has to be equal to that term. These coefficients have to be equal. Similarly, if we go exchange A1 with A2, then this becomes an A2 and an A2. And that corresponds to this A2 and this A2. So that means this coefficient and this coefficient have to be equal. So this guy and this guy have to be equal. And finally, this coefficient and this coefficient have to be equal by the same token. And so you can write this now in a more compact form or nicer form, simply like that. So let's write our final answer. dA1 by dt is equal to mu A1. And let me, excuse me, let me write it as, let me see, should I factor out the minus sign as yeah, let me write this now as minus A1 times A1 squared plus G A2 squared. Where I'm assuming that, well, I'm not assuming anything, but later I will assume A is positive, and so I have a supercritical bifurcation to stripes. Right now that is not of any significance. I just choose it because I want to use the equation in that way later. Okay, and so for A2 we have a very similar equation, which looks like G A1 squared plus A2 squared. So we know that what we need to calculate, if we really wanted to know specific results for a specific system, like for our PDE, we have to calculate three coefficients, G, A, and mu. Okay, but we don't want to do that here. Instead, in the next step, let's just analyze these equations and see what kind of solutions they have depending on what the coefficients are. That's, again, somewhat of a calculation, so we'll not do it right now. We'll postpone it till next time.